Right, here's another step question, this time gravitational fields, but slightly differently. It's quite interesting here. Flat Earth Society arguments. Is the Earth flat? Or if it were, could you work out what the gravitational field is? So simply explain what, let's go for it. Explain what is meant by potential of a point in a field of force. The potential, well, I suppose the potential would be, let me write it up here so I'm not using up too much space. The potential would be the energy required in order to bring a point mass from an infinite distance away towards a point of separation from the center of this object of R. So I've written that in code pretty much. So therefore, in other words, you'd say the potential is the integral of the work done from an infinite point away to a near point of zero, the work done. And the work done here will be, sorry, what am I talking about? Sorry, it's be the integral of the force with respect to the distance from an infinite distance away towards R. It's just a definition, so I won't ponder too long on that. However, it says, in the field, due to a positive point charge, the electric field decreases, whereas the gravitational potential increases. So I suppose the reason why here is because gravitational force is always attractive. So the force, the direction of the force in this instance was that way. And it was a point mass that we were considering, and this is a much larger mass. So that's an attractive force. That means that in order to reach this point of r equals infinity, which actually has a potential of 0, as we're forcing this away, we're putting work in to get to an energy point of 0, so therefore this must be negative. Whereas with an electric field, we always consider the electric field as a positive one, and the point charge, sorry, Q, and the point charge as well as being positive. So there, the force is acting out. So you wouldn't have to put force into it in order for it to reach a potential distance of away of infinity. So it's more about one is attractive force and the other is a repulsive force. Right, let's get to the gutsy question here. Flat Earth Society, this potential here represents the potential at a point away from this annular disk along H. For points of the axis very close to flat Earth, the gravitational field can be considered to be uniform. Use the relationship quoted to find an expression for G on the axis as you're moving away. Okay then, right, so how are we going? Let me give you a hint first on how you might go about this, and then I will show you how you can go about it. So what are we going to do? We are going to look for, you are going to find an expression G from V, and you're going to use the idea that G, of course, is the potential gradient, dV by dr, for when H equals 0. Or should I say, because we're moving along H, I should call it dV by dH, because you're moving up here. So that's your hint. Try that and equate it to H equals 0. And here comes the answer. Just need to find the paper. So how are we going to do that differential? So d by dH is going to give me G. I know it's a negative, and I need minus, so let's get the minus out of the way, 2gm over r squared, h squared plus r squared, rooted minus h. Okay, how do we do this? Well, we have a product here, first of all, so therefore I can deal with these ones separately. No, actually, sorry, forget what I said, that product. We can just, how do we deal with the inside of this bracket? Okay, so when you differentiate, you take this one, gm over r squared, all as a constant, so there's no problem there. We differentiate what's inside there and the factor on the outside. So that gives me 2h across the top. and inside here it's going to give me the square root of h squared plus r squared. Well, sorry, take that out to the minus a half because I've had to reduce the power of this by 1, so from a half to minus a half. And then I do the same again, but with the h, so really the same factors come out. I'll have minus 1 in there because when you differentiate h, you get down to 1 in effect. Differentiate dh by dr, dh, it gives me 1. Okay, is that done? Oh, and because because I had a power of a half, I need to multiply by half. So that's divide by 2. So I have taken the power of the top down, and then the factor, reduced it by 1, and then I've taken inside, of course, because it was h squared, I've differentiated that out, and that will give me the endpoint. Okay, then so that's g. And then we want to see what happens when, if h is 0, because that's what it's asking for, then we have, where does this drop out? 2gm over r squared by, the 2's obviously drop. If h is 0 there, and I have a, so we're coming back to this, we're coming onto this bit here. I need to substitute when h equals 0, so therefore that puts me with h at the top of 0. Well, this just turns into 0 in effect, because I've got an h there and an h there, but you can ignore that, turns into a 0 minus 1. So that gives me minus 2gm over r squared. There it is, the endpoint. So that was the first point here, and then it asks, so that's the gravitational, that's g at the surface. So the next part then asks, it says the magnitude of mass m of a flat Earth is to be fixed so that the gravitational field strength h0 is equal to that of Earth. So find m in terms of me. This is so straightforward, I'm not going to give you a hint. You know that g on Earth is minus gm over r squared, and so therefore, if that's the mass of Earth, what does m have to be in order to mimic this? M must be me over 2. If I substitute that into there, it would give me the same as that on Earth. Okay, easy, straightforward. Right, but where are we up to next? It's getting trickier now. Suppose a rocket were to be projected vertically upwards along the axis to a point R. So let's imagine from there to a point R. Neglecting errors is to calculate the required speed of projection from the Earth's surface, from the flat Earth's surface. So we know this expression here. I'm going to work on this bit here. So what you need to do is you need to substitute in, this is your first end, you need to substitute in from 0, from h equals 0 to h equals r, work out what the change is, obviously change, so we need to know the gravitational potential from h equals 0 to h equals r, and then you need to equate the kinetic energy to the change in potential times mass and work out an expression for velocity. Well, it sounds simple. Okay, there we go. If you think you want to give it a go, try it. Otherwise, here comes the answer. So we are working from, first of all, at h equals 0, v equals minus 2gm over r squared, 0, so that leaves us with r squared, well, I'll write it out anyway, root 0 plus r squared minus 0, giving us 2gm over r squared, but I've got an r at the top there, over r. At h equals r, then v is minus 2gm over r squared, I will have in there an r squared plus an r squared rooted minus the h would be r, giving me minus 2gm over r squared. Let's bring an r out of everything, because an r would drop out to there to be 2 root 2r minus r, which would be, take one of those out, and that should give us root 2 minus 1. Good. Now we're looking for the difference between the two. So the difference between the two, let's call it 0 and r, is going to be, the difference is, just thinking which way round I want this. I want it as, I want the final point, VR minus V0, giving me minus 2gm over r squared. Let's take that constant out the whole time to make life easier. And I want the root 2 minus 1 minus 1, giving me minus 2gm over r squared root 2 minus 2. That's looking good for the meantime. So my half mv squared is now going to equal delta Vm. We can get rid of the m's. V is going to be equal to 2 delta V square rooted, which is not a small equation, but here we go. 2. Let's get rid of that minus sign there first by rotating it around. So let's just say it's 2gm over r squared 2 minus root 2. Might be easier. So there we've got two lots of 2gm over r squared 2 minus root 2, all square rooted. And of course, what I need to do now is, okay, let's keep following this through. So this is, just looking carefully here, this is m of this object. I don't know the m of that object, but what I do know is the mass of the Earth. And from my previous equation, I know that m is the mass of the Earth divided by 2. So what do we have? Let's plug some values in, that's probably better. So we have 4g over r. Whoops, why did I write r squared there? Because that should be coming down to r. Then obviously I've got my, so 4g over r. Then I've got my m, which is the mass of the Earth over 2. And then I've got my 2 minus root 2, all rooted, giving me, let's just bolt in some numbers here. Take the 2 with that, represents 2, so that's 2 by 6.67 times 10 to the minus 11 by the mass here, 6 times 10 to the 24 by 2 minus root 2, divide that by 6.4 times 10 to the 6 and root the whole thing. And if the sums I did previously came out correctly, meters per second. That's how fast you'd have to eject it by. Right, okay, coming back. Quickly turn over. We're ignoring this question here, it's just this one to finish. Right, we are aiming to prove this first expression back here, in effect. What's the potential? We are looking to work out that from looking at this sort of volume element around there, and then integrating up the entirety of it to then work out the potential. So I suppose the clue which you need if you want to give this one a go yourself is, let me think about how I'm going to word this one. You want to probably first of all try and work out the volume element, and therefore the mass. This thickness one might catch you out. How are you going to work out the thickness explicitly? And then you want to then integrate it up, but you'll need to do that by parts. So you'll need to integrate up your expression for, so you'll need to move from there to there, but you'll need to do it by I forgot the mathematical term, is it by substitution? So you need to integrate by, so volume element first and then the mass. In order to get the mass element, you'll need to work out how to approximate the thickness, and then you'll have to substitute to make the integration better when you move from one edge all the way to the center. Good. If you've tried those three things, you might want to try those three things yourself. But if you're feeling a bit lost, here comes the solution. Good. So here we have a ring, and the gravitational potential from that distance there is going to be minus gm over r. However, the mass element of the ring is going to be first of all, the circumference by delta r, but then you need a thickness as well to that, and you need the density of the material you're talking about. Where's that thickness? Well, if we say that the thickness is going to be the total, is going to be the volume divided by the area, total volume divided by total area, and we know that the total volume is going to be the density divided by the total, the mass divided by the density, then an expression for T is going to be the total mass divided by the area divided by the density. So we plug that in, 2 pi r dr density m over pi r squared rho. Okay, not an easy expression, however. So therefore, we're coming to the change in potential is going to be minus g 2 pi delta r, the rows cancel, m over pi r squared, I forgot the r there, by r. But we know that r is going to be this distance here, and so therefore it's going to be a bit of Pythagorean algebra to get that. Minus g 2 pi dr m over pi r squared h squared plus r squared square rooted. Good. Now, if we've got to integrate out, that's going to make life a bit tricky. So let's put in a substitution. Let's say that z squared is equal to h squared plus r squared. So that 2z dz is going to be 2r dr, because of course this is the variable we're interested in. We're moving along with r, h is a constant in effect. And therefore we have r dr is going to be z dz. So can we see that the r dr, right, we need to say that delta v is going to equal now 2 gm over r squared, 2 gm over r squared, these cancel, divided by dr is going to be z dz divided by z. Z dz divided by z. Good. Next step. So, the z's of course cancel out, leaving us with a simple minus 2gm over r squared, integrate up dz between the limits of 0 to r, because we're moving from the centre of the disk to the outside of the disk, which gives us very simply a minus 2gm over r squared z, because that will be 2gm over r squared z between the limits of 0 and r. But of course z is going to be, because we look back for our substitution, h squared plus r squared. So to the half, and those limits are r to 0. So the final step is v is going to be minus 2gm over r squared, h squared plus r squared, square rooted. Then, of course, you have this second term, so I've just placed it all in there, minus, and I've put a 0 in. The r is obviously this way, just leaving us with h squared, square rooted, h QED. That brings us back to first expression there. Okay, so a bit tricky when we have to do the substitution as well, and when we have to work in, all the necessary bits, but hopefully that makes sense.